Hello, calculus fans! We're going to talk about some vector forms of Green's theorem. Now, it may be helpful for you to go back and just look up what Green's theorem says before we go on to discuss these vector forms. Now, the curl and divergence operators allow us to rewrite Green's theorem in versions that we're going to be able to use later. Now, let's suppose that we have a plane region D, a boundary curve C, and functions P and Q, all of which satisfy the hypotheses of Green's theorem. And let's create a vector field, F, which has components P and Q. Now remember that the line integral of F around the closed curve C, which we can write as the line integral of P dx plus Q dy. And if we think about F as a vector field on R3 with a 0-third component, then we can write down the curl of F. The curl of F will work out to dq by dx minus dp by dy times the vector k. If you look carefully, the I and j components will come out to be 0 because you end up taking derivatives with respect to z of p and q, and those are going to disappear. Now, this piece in here, since you've refreshed yourself on Green's theorem, should be familiar. So the curl of f dot k will end up being dq by dx minus dp by dy. So again, this expression is the thing that comes out of Green's theorem. So what we're going to do is we're going to rewrite the equation in Green's theorem in a vector form. So what we get is that the line integral of f along the curve C is equal to the double integral over d of dq by dx minus dp by dy dA. And so we can rewrite that as the double integral over d of the curl of f dot k. So this first equation here, that's what Green's theorem told us. What we're doing now is rewriting the integrand as curl of f dot k. So in the end, the way that you really should remember Green's theorem is by setting these two things equal to each other. So it's really these two that are equal, and then you can not worry about remembering this dq by dx minus dp by dy thing. So this expresses the line integral of the tangential component of f along the curve C as the double integral of the vertical component of curl of f over the region D enclosed by C. Now, if you keep this in mind, as we move forward and we talk about Stokes' theorem in a couple of sections, this will come back into play. So what we'd like to do now is derive a similar formula involving the normal component of f. So we just dealt with the tangential component of f, now the normal component of f. Let's suppose now that our curve C is given by this vector equation r of t. So it has components x of t and y of t. So this is a parameterization of the curve. The parameter values go from a to b. And we can compute the unit tangent vector, and it'll look like this. So you might need a refresher. You might want to go back and look up how did we compute the unit tangent vector. And it's also not hard to verify that the outward unit normal vector to the curve is given by this. So first of all, this is a normal vector, and if you dot this with the tangent vector, you'll get 0. And that's what you want for a unit outward normal vector to the curve. Let's look at a picture to see what are we talking about when we're discussing the unit tangent and the unit normal vector. It looks like this. So you've got a tangent vector, which runs tangent to the curve, and you have a normal vector, which runs normal to the curve. Now this is a little bit different than the unit normal that we talked about before. This particular vector is an outward unit normal vector. This will come into play next section when we start talking about surface integrals. So now, let's compute the line integral of the normal component of f along the curve C with respect to arc length. The way we write that is like this: line integral along C of f dot n ds. So the way we compute that is the integral from a to b of f dot n times the length of r prime of t dt. All right, go back and look at what f was, look what n was. We dot them together and then times the length of r prime of t. This is what we'll get. Now this looks kind of messy, but the good news is a bunch of stuff will cancel out. Now we get a much easier looking expression: p times y prime minus q times x prime. Well, that's just p dy minus q dx. And according to Green's theorem, that's the double integral over d of dp dx plus dq dy integrated with respect to area. So that last equality comes from Green's theorem. Notice that the integrand in the last expression is just the divergence of f. All right, so now we have a second version of Green's theorem. Looks like this. The line integral along C of f dot n ds is equal to the double integral over d of the divergence of f with respect to area. Okay, that's all for now.